Although partial fraction decomposition is not exclusively covered in calculus, it tends to be a challenging concept for many students, so I'm going to briefly walk you through the basics of solving integrals using partial fractions. Keep in mind that this method only works when you have a rational function in which the degree of the leading term of the numerator is less than the degree of the leading term in the denominator. Let's look at the integral of x minus 1 over x squared plus x. Our first goal in any partial fraction problem is to factor the denominator so that we have at least two factors being multiplied by one another. When we factor in x in the denominator, we're left with the integral of x minus 1 over x times x plus 1. Our next goal is to break apart our rational function into two separate fractions, which are going to contain one term each from our original function in the denominator. What we're trying to do here is find two constants, a and b, that when added together gives us our original function of x minus 1 over x times x plus 1. What we're doing is basically working backwards. Up to this point in math, we've been taught to combine functions in order to simplify them in one expression. But now we're trying to break apart that expression into a series of smaller functions that are much easier to integrate. To do that, we need to arrange the expression as follows. We then want to multiply both sides of the equation by the denominator of our original function to get rid of any fractions we might have, which brings us to the next part of our calculation. To solve for a and b, we need to plug in values of x that will cancel one of our constants, either a or b, leaving us with only one to solve for at a time. To solve for a, we set x equal to 0, and what we're left with is a is equal to negative 1. To solve for b, we set x equal to negative 1, and find that b is equal to 2. We can now take the values of our constants, a and b, and plug them back into our separated fractions, which will allow us to solve the integral. Once we break apart the integrals and rearrange them slightly, we're left with the integral of 2 over x plus 1 minus the integral of 1 over x, which we can calculate without too much trouble. Our final answer should be 2 times the ln of the absolute value of x plus 1 minus the ln of the absolute value of x plus c. Here's another example. Let's find the integral of x plus 7 over x squared times x plus 2. Whenever we have a term in our denominator that is raised to some power, we say that that term has a repeated linear factor. When this is the case, we have to build up to the degree of that repeated term when organizing our partial fraction. Here's what I mean by that. Notice that we have an a over x plus 2 plus b over x plus c over x squared, instead of just a over x plus 2 plus b over x squared. You'd expect that since it appears that we only have two terms in our original fraction of x plus 7 over x squared times x plus 2, but really what we have to do is we have to, as I've said before, we have to build up to that term, which in the case of x to the fourth power, for instance, would mean having a over x plus 2 plus b over x plus c over x squared plus d over x cubed plus e over x to the fourth power. That's what I meant by building up. And once we get past this, the rest of the problem is just following the same steps as before, multiplying both sides of the equation by the denominator of our original function, simplifying each term, and plugging in x values to solve for our constants. Part of the reason why these types of problems can get really complicated is that it isn't always clear when you have repeated terms until you've completely factored the denominator. But if you're ever discouraged by how long these problems take to solve, just remember that there's a reason math majors tend to have little trouble impressing all their friends. So the first two values we chose for x are pretty obvious, but the third value we choose for x is more of a matter of preference in this case. When we set x equal to 0, a and b are cancelled and we can solve for c. When we set x equal to negative 2, b and c are cancelled and we can solve for a. And by the time we solve for our last constant b, it's no longer necessary to cancel out the other two terms since we already know their values. I chose x to be negative 1 because it's a number that we haven't used yet and it's fairly simple to use in our calculation of b. Now that we have our three constant values, we plug them back into the integral and we're ready to finish up the problem. Using straightforward rules of integration, we split our integral up into three fractions and evaluate them individually to get negative 7 over 2x plus 5/4 times the ln of the absolute value of x plus 2 minus 5/4 of the ln of the absolute value of x plus c. By the way, don't confuse our constant c here with the constant we used in our partial fractions. They aren't equal to each other. I just forgot to switch up the notation. So now that we've made it through these tedious partial fraction integrations, it's important for us to look back on some of the things we learned throughout the video, maybe some of the realizations we've come to along the way, which is why we're going to recap everything we went through. So step one is to factor the denominator. Here you want to decide if there are any repeated linear factors and proceed with the problem accordingly. Step two is to break the integral up into the number of parts based on how many terms there are in the denominator. And step three is to solve for all the unknown constants by plugging in different values of x. Once we have these values, we can plug the constants back into the integral and evaluate it.